Hi everybody, good morning. Thank you so much for coming. We have a very, very busy day, so we will need to get started straight away. Just a few points. I just want to say, first of all, huge thank you to our interpreting team. Obviously, a lot of this content is very technical, and unfortunately, we didn't have all the materials available in advance, and so I just want you to take that into consideration. If you have feedback for the interpreters about the content or any of the terminology, please grab one during a break and have a chat with them about that. That'd be fantastic. It's going to be a busy day. We're going to have to rush a little bit, but we're trying to get everything done in time and ensure that everybody has a good chance for the breaks. On the program also there's a QR code where you can also use an app to see some live captions. It's a bit experimental, so feedback on that would also be appreciated. Okay, so first of all, we're going to start with Professor Richard Bowden. Rich is a professor at CVSSP, where he leads the Cognitive Vision Group. And he's been working in sign language for over 20 years. Yeah?
If you like.
And today he's going to give a presentation on some of the work that's going on at the University of Surrey and also on the Sign GPT grant that he's leading. Okay, so please give Rich a warm welcome.
Okay, thank you. I'll try and go fast, but I can only go as fast as our poor interpreters. So I stole the title from the workshop, cheekily, because I thought you put me on first. And I think we also talked about getting Bensi to come and do a bit on sign, but I've kind of rolled that in as well. So there's maybe I'll talk a little bit about sign language just to set the scene for the day. Overview for the talk, but it's a waste of time as spending any time looking at that slide. So we'll just we'll move on to the practical. Now this slide is not for the deaf participants. This is for hearing researchers, really. And I always find it's getting, well, start with dispelling some myths. So what sign is and what sign isn't. I'm guessing I'm preaching to the converted because everybody here is either a member of the deaf community or actively working with that deaf community. So, but we'll go through it anyway. So sign, obviously it's a visual language. It's a native language of deaf communities. Importantly, it's the first and primary language for the deaf. And it's amazing how many times you get asked the ignorant question, which is why can't they just read subtitles? You know, which misses the entire point. So you know, it's the primary language of that community, and there's lots of historical and cultural reasons why accessible information in sign should be provided. Another one that seems to constantly surprise hearing people is that every country has its own sign language. What? There isn't just one? Absolute madness. Well, you know, but of course there's different languages. Languages evolve through interaction between people, and different communities evolve their own languages. But of course, you know, we also know that even within a country, we can have huge regional dialects. So from a computational point of view, this becomes an incredibly difficult problem to solve, just because of the variability. Also, there's no simple mapping from spoken language to sign. So, and we'll look a little bit about this translation process and the transition from moving from recognition systems to translation systems. It uses both the hands, but also non-manual features and space. The grammar is completely different to English or spoken languages. Space is used in different ways. And all of these things mean that it's not just a simple translation of words to signs and vice versa. And this is probably the most important thing, is that members of the deaf community don't necessarily see themselves as disabled. You know, they are proud members of a linguistic minority. And again, sort of the hearing world tends to come along not knowing anything about the problem they're trying to solve, not knowing anything about the community that they need to work with. But I think that the deaf voice is getting stronger. And so it's important that, you know, that we stop this, that the fact that that too much work happens without the involvement of the deaf community. Right, so who here is a hearing researcher who works in sign? Put your hands up. Okay, leave your hand up. Hang on, put your hands up. Leave your hand up if you have gone and learnt sign language. Okay. So there was a few people there that put their hands down. And I think the key thing is, and we increasingly see this, is that hearing people come in and they just go, oh, it's just gesture recognition. I'm going to solve the problem. I'm going to take my technology and I'm just going to apply it. And they don't even know what the problem is that they're trying to solve. And that really, really alienates that deaf community that you should be working with from the outset. So I've done the political piece now, right? So now we're all educated. Well, I'm sure I was preaching to converted anyway. So a few years ago, I put together a timeline of computer vision. So I'm going to start with that. I'm the first of the day, so I'm setting the scene. At least in my head, I am. I wasn't asked to set the scene. I'm just. But computer vision started in 1966, or at least if you search on Google, right? So Minsky, MIT, set computer vision as a summer project for a student. By the end of summer, he will have solved computer vision. The machine will be able to see. We'll fold that into AI, and we'll all move forward, right? It turned out that it was a little bit more tricky than just a summer project. If we want to go back a bit further, we could probably trace it back to the kind of early 50s with work on optical flow. But before 1950 is termed BCV. And this stands for before computer vision, right? So before 1950, there was nothing, right? There was just, if you understand the reference, a monkey in a desert with a bone banging on a big black obelisk. There was no technology, there was no science, there was nothing. Yeah. And then I've taken all the animations out to try and make this slide a bit more deaf-friendly. But so you don't read these. But these, from a computer vision perspective, are kind of papers that we would recognise over the years. Just important points are around here. This is where computer vision entered the living room with things like the Microsoft Kinect, slamming a vacuum cleaner. So that was great. Actually, computer vision started to find its way into products. But if you want to, this is where I came in. So it depends who I'm talking to, whether I'm old or young. But I started my PhD in about 1995. If we want to categorise this field, then it's been through various stages. So it started off as kind of AI. Back in the old days, back in that lab at MIT, we then stopped using the term AI. It went out of fashion for a while. It all became about projective geometry and things like that. Andrew's written all the textbooks on that. I remember when he changed, he sort of said, oh, it's all solved. I'm moving on to a new area now. Projective geometry solved. We went through machine learning, big data, and then we've got this deep learning revolution now. So it's all about neural networks and it's all about big data. Off in the future, we've got the singularity, right? So at some point, and this is what we're all scared of, at some point, the machines take over. So one assumes that between now and the machines ruling the world, we will have solved sign language translation. Okay, so at least we've got an upper limit, the 2045, when we know it's going to be solved by then. So the question of today is, how much sooner than 2045? Now, I've done a similar timeline. Sorry, should be paying more attention to the interpreters. So a similar timeline for sign language. So I started in 1995. There was a paper by Thad Starner that came out of MIT in 1995. This was probably one of the earlier examples of an automatic system for sign language recognition. Had the pleasure of meeting Thad at a conference maybe 6 months ago. Some absolute classic quotes came out of Thad's mouth. One was, I started the field, I'm going to finish it. Okay. So, but, there's a couple of other names. So some of you, Christian Vogler, who's now at Gallaudet. Christian did as part of his PhD, he was doing some early work on again, sign language recognition. And then I've not gone into anywhere near as much effort putting things on this timeline. But there's just some key things. So 2012, Oscar Koller, the Archon Group, the Phoenix data set sort of came into existence, and this was a weather corpus. So quite a small data set, very constrained domain of discourse, but it's hugely helped the field because it gave us something that we could work on in terms of translation recognition. I remember, I mean, when it was released, the error rates were like 80%, and then it didn't take long before the error rates were 20%. So there's also, I mean, Oscar's seen this slide before. 2016, I think this is a turning point because this paper combined both older HMM technology with modern deep learning. So it's kind of a transition. And then we've got a translation version of the Phoenix data set, some work that came out of our lab with Jihan, where we started to apply neural machine translation, NMT, to the problem. And then the timeline kind of goes, it's just about more data. And again, if we want to categorize this, then we could sort of like categorize it. It's very early years where we're leaning heavily on speech with HMMs, and then we went through similar phases. But really, since neural networks came in, we've made a transition from what I would say recognition to translation. And I'm going to come back to this idea of the distinction between the two shortly. Now, I said that a lot of the emphasis has been on data sets. And this is a good visualization that Erzga did for a paper that looks, there's that Phoenix data set. And the size of the circle is how big the data is, but it's also how well it's been annotated. So things like MindDGS, which comes from Hamburg. It's amazing how many old faces are in the room today. But MindDGS and the BSL corpus, which comes from DCAL, these are linguistic data resources. So they're very well curated, but that means they're small. They're small because it takes huge amounts of effort to curate that data. Whereas what we're seeing now are these much larger data sets, which are collected from broadcast television or harvested from Google. And this is just huge amounts of data, but very poorly curated and with very little annotation. And that introduces real problems. Part of the problem is to do with gloss and annotation. We'll talk a little bit about that. But part of this is also to do with whether it's interpreted or native data, right? And actually, a lot of the large data sets we're working on is interpreted data. And this is creating huge amounts of anxiety in the deaf community because that's not natural data. If you think about the interpreter's job, is incredibly difficult. They're trying to keep up with me, and I'm talking too quickly. I'm sorry. And so things get lost, and they're doing their best to try and keep up with this ignorant presenter. But that's very different from natural data that's coming from spontaneous conversation or from, or even a translation where somebody has taken a body of text and thought about how to restructure that into a native sign language in order to get the message across. And you talk about the prep work. The prep work is trying to help the interpreters do this incredibly difficult task, which is doing it on the fly. But there's huge amounts of difference between these two. And so the large data sets that we're getting are not indicative of natural sign language. And that, like I say, is creating huge anxiety in that deaf community about what does that mean for the future of AI? And these are all the things that we need to be worrying about. Now, we're academics, we're funded. I have to thank the funders. I'm going to show you 3 slides. I'm not going to expect you to read them. There's too much information on them. So I'll put them there and just concentrate on the interpreters, and I'll just say a few words about each project, and then we can move forward. So the first one is a Swiss project, which is just coming to an end. This is a collaboration with the University of Zurich. It's kind of a long-standing collaboration that's been on for a while. The focus around this project is really about language learners. But this project is coming to an end. But funders like to be thanked for their contribution, so I've got to get these in. We've also got a grant which is funded by Google, and this is about reducing the cost of translation. And this is working closely with Synapse. Ben's also in the audience. I think Synapse are talking later, so I'm not going to talk much about their technology, but Synapse is closely linked to the university. I'm one of the founders, co-founders, and Ben did his PhD with me, so it's a spin-off from the uni. Like I say, it's about bringing the cost down. I'll show this video just because it gives you a sneak peek at what Ben will show later. So this is Marcel Hirschman. This is a human, a translator, deaf translator.
Can I ask you to pause while
Yeah.
people look at the video?
Yeah. Well, maybe I should explain first. Sorry. So when you see, basically it's all the text becomes hot linked. When you click on it, you see a translation. When we see Marcel, This is a human interpreter. But when you see the female, Ray, her name is, that's entirely synthetically generated. And this project is about trying to provide cheap and affordable, accessible information. It's not about replacing humans. We're never going to be able to do that. The subtleties of human interpreting and translation will always have its place, but this is about trying to increase accessibility. So I'll play the video now. Okay. So like I say, when you see the female, that's synthetically generated, and Ben will talk more about that technology later. The third one is SignGPT, and that's today is funded by the BMVA, but it's closely linked with the project. We had a deaf space event yesterday, which was about trying to encourage more of the deaf community into the research program. And today is there's a lot of overlap. So a lot of the people that were at the event yesterday are also here today. But this one is a little bit more hearing, or let's say mixed communities. SignGPT aims to progress translation, primarily in BSL, because that's the language that's closest to my heart. But if we can make progress in one sign language, then we can make progress in many. But in both directions. So we're interested in building systems that can translate from spoken language to sign and from sign to spoken language. And that's where I wanted to talk a little bit about the distinction between recognition and translation. So on this slide, what we have is a sign language video, and then what we have is what the linguists would call gloss. And this is just a very simplified version of what's going on. It's basically from here to here is this sign. So name, me, Rich, right? 3 signs, but that forgets about all the non-lexical items and the use of space. It's a very simplified representation. And up until that transition point, pretty much all the work was recognition. It was going from video to isolated glosses. Whereas actually what's happened over the last 5 to 10 years is that we've opened this kind of the possibility of doing full translation, right? And you can see, so if this is recognition, then this is the translation, where we're going from a sign language video all the way to the spoken language equivalent. I put some arrows in here to show that there is reordering. So it's not just a simple word for word replacement. But like I say, actually this gloss is a very oversimplified representation anyway. On that timeline, to those key papers, let's focus on this one. This is a transformer-based translation system. So video comes in and spoken language comes out. It's as simple as that. But what you spot is that this gloss is here. And what we find is that if we try and train these systems end to end, going from spoken language, from video all the way to spoken language, it's just too much, right? It doesn't work. And so typically what made it work was we started to condition the networks on some sort of gloss data. And that kind of made it a little bit easier, because now it can start to learn the relationship between the video and this kind of the signs, and then it can learn from the signs through to the translation. The problem is, as I said, going back to that data, if you're going to harvest data off the web, you've got no gloss, you've got no annotation, and annotation is incredibly expensive to get. So what we want to do is we want to break our reliance on gloss, but also we want to increase the amount of annotated and well-curated data out there, specifically on that L1, on native rather than interpreted data. So these are all of the things that are of interest to me. Now, I'm just going to go through, so we've been working on this for a long time. I think this year alone we published 27 papers on sign language. So I'm not going to try and go through everything, but there's just a couple of examples of some of the stuff we've done this year to show the things that we're working on. So first of all was Ryan's sign rep, and this was about trying to learn a representation that was invariant to people, right? So that we can let's go back to that recognition, to be able to sort of like to say that these two signs are the same thing by two completely different people. I'm interested in this because I'm interested in using dictionaries. You know, if I want to gloss my data, and I want to be able to compare my lexicon that we've curated against that data, produce that gloss. We've also been doing some work on segmentation. If you I go back to that example, name, me, rich, right? If you look at what's going on there, actually the hand shape is consistent throughout each sign. Name, me, and rich. And so you could, in a very coarse sense, you could sort of say, well, if you could detect the changes in hand shape, then that would probably be a very good proxy for working out where the transitions in the signs are. And this is exactly what the linguists would say. It's not true, because some signs have more than one hand shape in, but as a coarse approximation, it works well. So I'll show you the video here, and this is just using, I think it's Willow or Hammer, one of the off-the-shelf hand trackers to track the hands. And then from that, we can basically work out where the transitions in the sign are. So I'll just show the video quickly. Okay, so it looks like they're wearing blue gloves. That's just computer graphics rendering the hands over. But what we're looking for is these changes in the hand shape. Ooh. Now we've taken this one step further. And so now we can break the continuous video up into candidate signs. What I want is a representation over a whole sign. I don't want to be feeding thousands or millions of frames into a neural network. I want to try and get representation that's closer to language. So we've been looking at how do we represent signs that the machine can understand. This was some work that Leo did called Sage. We also improved the hand segmenter, so now we don't need any skeletal data at all. We can just do it from those tracked hands. Ed's just back from Eurips, and he had a paper there, so I'm giving a plug to him, called Geosign, and this was really looking at alternative representation. So again, like that sign rep, we know we can put inductive priors in. We know what's important, so we can make sure the machine is focusing on the hands and the face and the body, and then this was about learning better representations for the machine in order to kind of tease apart the representation. We can put some of these things together. So in this video, what you're going to see along the top is an English translation for a sentence. And then we've used the sign segmenter to automatically, from a continuous sequence, find out where the individual sign candidates are. And then we've used the sign rep to basically go to a dictionary and look up what is the most likely sign candidate for each of those words. And so when I play it, it'll play the video, and we'll see. So these predictions here are automatic. There was no user intervention. They're not perfect. I'll just stop it there. So there's a good example there where it's doing hospital. So you can sort of see that up here, it's identified this sign as hospital, but it also thinks it could be parcel or basket, because actually visually they're very similar. And what's missing from this is the intelligence that is in the linguist, the fact that we use context. So the next stage to build on this is when we're working on how do we build context into this, we're effectively trying to build a co-pilot for linguists. Something, think of it as, excuse me. Think of it as a PhD student in a box that you can send off, and instead of them spending 6 months doing a study, they can do it for you in a couple of hours. And then the PhD, of course, can do something more interesting. Now, everything I've talked about so far has been manuals. We're also interested in lips and faces. So we've got work going on in the lab in terms of production for faces. We also Marshall have done some work on lip reading. The reason we're interested in lip reading, of course, is not because I care about reading lips, but because we know that non-manual features and mouthings are a key part. And so when we build recognition systems, we get huge performance increases by including mouthings into them, which is not surprising if you know anything about sign. So, there's lots going on in the lab. In terms of 2D generation, now Ben's going to talk about GANs, generative adversarial networks, which are kind of a little bit old now, but it's understood technology. A lot of us are playing with things like diffusion models. So here is a diffusion model that allows us to change the appearance of the signer. If you are a 14-year-old female with X demographic, why should your interpreter look like a white middle-aged man? You want to be able to choose. But now we get into lots of ethical problems about choice. Who has the choice? The choice should lie with the stakeholder, right? The person that's consuming it, not with the person that's actually providing it. And so, but there's another day for the ethics around that. Now, part of the problem is a lot of these models are trained on hearing data. Now, who's a BSL user? Okay, I'm going to show you a video, and I want you to tell me what he's signing, right? Anyone? No. Why is that? If I show this to a hearing person, they go, "Oh, it's amazing! Looks like he's signing." If I show it to a deaf person, they say, "Can't understand a word of it." And the reason they can't understand a word of it is that the diffusion model has destroyed the content, right? Because it was trained on hearing data. Now, this came from this. So I'll play you the original. You understand what's being said? Okay, and compare the two, right? So I need to stop it. So the manuals are good, but it's the non-manuals that are being destroyed. And again, I think this is because it's been trained on hearing data. Quite often, it just introduces babbling, right? Because that's what hearing people do. They babble. They move their mouth a lot, right? And that's not indicative of sign language data. So again, it goes back to the fact that we need to be very mindful of the data that we're using to build these systems, because we are going to introduce biases. We've also done some work in 3D. So in the studio, all the data that we capture in 2D, we can also reconstruct in 3D. There's an example here, which I'll show, which is Rachel reconstructed in 3D. And then we can stitch data back together, and because it's all done in 3D, that reduces a lot of artifacts. So I'll just play those. And then final plug, which is also Maxim. We've done some work taking those diffusion models that allow us to control appearance, but doing it in 3D. So here we can give a textual description of what we want the avatar to look like, and then it can generate that demographic or that clothing. And the animations, are the same. It's just the appearance that's changing. But this diffusion process is happening in the 3D model space. Now, so this last couple of slides, right? So part of the problem is that we use, for want of a better word, crap metrics, right? Because things that don't actually measure what's important. And there's no real substitute for a deaf eye, right? So, but doing deaf intelligibility studies and things is incredibly difficult. So one of the things we're trying to do is rethink how do we assess things like production. At the moment, we use something called back translation. So we use a recognition framework in order to judge how good production is. But recognition hasn't been solved, right? So we're using a flawed system in order to try and judge how good a production system is. So it's no wonder that when we then go out to do the user trials, the deaf participants go, "I can't understand a word of it," right? Because it's not measuring the right things. So we've looked at trying to, this is the SAE framework for autonomous driving, right? So down here you've got no automation, up here you've got full automation. We've done a very similar thing with sign, and so we've got this tiered framework where here is just human translation. Up here is our fully automated sort of like translation. It's as good as a human. We'll never get there, doesn't matter, right? Because actually tier 6 is where it's important. And this is about having technology that we can put in the right places. And so I thought that he was like kiboshing me. So, and for things like, so I'll just give Ben a bit of a plug for later on. So when he shows examples for the transport sector, in terms of production, we're already at tier 6, whereas actually for unconstrained translation, we're a little bit lower. But importantly, this framework is assessing quality in terms of the things that we know are important, things like realism, grammar, use of space, non-manual features. And what I would encourage people is to start thinking about judging their technology in terms of what's important to the deaf stakeholder and not in terms of back translation and things like that. So this is the last slide, right? So I've talked about using skeletons, I've talked about using images. I'm not Google, I don't have infinite compute. And so actually the choices that we make in the lab is largely to do with what we have available when we're building systems. I've talked a little bit about gloss-free and large-scale data. I mean, Phoenix was amazing, right? We all loved Phoenix. But it's become the KTH dataset of sign language, right? And every single time I publish a paper, somebody says, how does it do on Phoenix? I don't care how it does on Phoenix. Phoenix is a weather corpus, and it's not indicative of translation. So we need to be moving to much better and bigger data sets. But those data sets need to be L1. We need to be mindful that actually what we're training on these large interpreted data has biases, has lots of issues, and it's not indicative of the real data. And I'm not sure how we address this, because one of the biggest challenges we've got at the moment is access to data and getting ethical access to that data. So data issue is a problem. We need better ways to assess. I've talked a little bit about better metrics. And then there's this deaf-led thing. And so yesterday we had this deaf space. This is it. I met some beautiful people yesterday. And if you're a deaf computer scientist or mathematician and you want to do a PhD in this area, we want you to come and do it in our lab. So that's it. Thank you. And I've probably got no time for questions.
Time for one question, please.
Don't worry, I'll be around all day.
One question.
No.
Nobody? Well, that's good for me, because we can keep a little bit more on time. Okay?
Yeah, just trippy.
Okay, so now we have Leo.
Use that.
Thank you.
Oh, yeah.
Thank you.
Yes, should it work? Okay.